All right, hey AP Chemistry, I'm going to try to go over how to do some problems on page 273 and 274. So before we get into actual problems, just a few things. So when you're talking about solubility, like if you had a compound like KCl and it had a molarity of 1 molar, then when it splits into ions, if the initial molarity of the compound is 1 molar, then the molarity of each ion is also 1 molar. But if we had a compound like CaCl2 that had a 1 molar concentration, when it splits into its ions, since calcium still has a 1-to-1 mole ratio, it will have a molarity of 1, but you're going to get 2 chlorine ions when it splits apart, so the molarity will be double. All right, so when we're doing these problems, you have to think about the coefficients, and is it 1-to-1, or is it 1-to-2, or is it even like 1-to-3? Like if it was aluminum chloride and we had a 1 molar concentration, then the aluminum would be 1 molar, but in this case, the chlorine would be 3 molar. Okay, so that's just some background knowledge. And then the other thing is that when you're doing KSP, it's the same as the it's the same equation as before. It's the concentration of the products over the concentration of the reactant. But this time the reactant is a solid, and so you can't actually get the molarity of a solid, so there is no denominator. So in this case, the KSP if you did KCl, the KSP would be the molarity of K times the molarity of Cl. If you had CaCl2, then it would be the molarity of Ca times the molarity of Cl, except this time it's going to be squared because you get a coefficient of 2. And if you had the KSP of aluminum chloride, it would be the molarity of aluminum times chlorine cubed. Okay? And so, and there is no denominator, all right? Because on each of these, the reactant is a solid, and so you don't put solids into the equation because you can't get the molarity of a solid. So what SP stands for is solubility product. So we're only using the products, not the reactants, to solve these. Okay, so if I look at problem number 3 on page 273, it says if the molar concentration of lead bromide in an aqueous solution is 1.6 times 10 to the negative 6, what is the concentration of lead and what is the concentration of bromine? It's the same idea as what I just did. It's just that instead of easy numbers with 1 and 2 and 3, we're using 1.6 times 10 to the negative 6. So what number 3 is saying is if you have some PbBr2 with a concentration of 1.6 times 10 to the negative 6, when this splits apart, the Pb is going to be 1.6 times 10 to the negative 6, but you're getting 2 bromines because every time it splits apart, you get 2 bromines for 1 lead. So bromine is going to be twice that. You're going to have 2 times 1.6 times 10 to the negative 6, which is 3.2 times 10 to the negative 6. Okay? So these are the answers. The concentration of lead is 1.6 times 10 to the negative 6. The concentration of bromine is going to be 3.2 times 10 to the negative 6. So that's where those answers come from. On number 4, it says the molar solubility of silver iodide is 1.6. So that's telling you the concentration of the compound of silver iodide. And then this time it wants to know what the KSP, the solubility product, that means KSP. So we're taking it a step further than number 3. So on number 4, let's just start by writing it down. So we have AgI, and it's going to split into Ag plus I ions, Ag plus and I minus. If this is 1.22 times 10 to the negative 8, then Ag is also 1.22 times 10 to the negative 8. And I is 1.22 times 10 to the negative 8. Since everything's a 1-to-1 ratio, all the numbers are the same. So these are the concentrations of the ions. So remember, KSP is going to be the concentration of silver times the concentration of iodine. So if I plug in my numbers, I'm going to have 1.22 times 10 to the negative 8 times 1.22 times 10 to the negative 8. And when I multiply that together, you get 1.49 times 10 to the negative 16. So the KSP is 1.49 times 10 to the negative 16. Okay, on number 5, it says it's a reverse problem. So on number 5, it tells you KSP is equal to 3.6 times 10 to the negative 29. Okay, these are tiny numbers. What that tells us is that they're barely soluble. Like if you drop a chunk of this into water, like one molecule will dissolve and the rest of it will stay as a chunk. It's not like salt that just dissolves in water. These are tiny numbers, meaning they're barely moving to the right. They're not very spontaneous. Hardly any of it dissolves. Okay, so if you were to get the KSP of, say, salt, it would be almost infinity because almost all of it dissolves. It moves all the way to the right. These barely dissolve, so barely any ions are going to form. Okay, so to actually get the answer, though, let's just do this in reverse. So if KSP is equal to the concentration of cadmium times the concentration of sulfur, all right, let's put the ion charges on there, CDS, then these are a 1-to-1 ratio, all right? So if you have CDS and it breaks apart into cadmium and sulfur, it's a 1-to-1 ratio. So these numbers are going to both be the same. So if I have 3.6 times 10 to the negative 29 equals x times x, because they're both going to be the same number, then x is this, you get x squared equals that. So x is going to be the square root of 3.6. So I'm going to do the square root of 3.6 times 10 to the negative 29, and I get 6 times 10 to the negative 15. So that's the molarity that each would be. So when these dissolves, I would get a molarity of 6 times 10 to the negative 15 molar for cadmium, and I'd also get 6 times 10 to the negative 15 molarity for sulfur. Like that's what it's asking. What is the molar solubility? All right, and so since each of these are a 1-to-1 ratio, then the molar solubility of the compound would also be 6 times 10 to the negative 15. So like that's where the answer comes from. Okay, if I keep moving on, now it's going to be a little bit more complicated. So on number 6, it's the same type of problem, but it's just one step harder. So here we have the KSP of strontium fluoride is 2.5 times 10 to the negative 9. What are the concentrations of each ion in a saturated solution? Also, what is the molar solubility of the compound? Okay, so let's just think about what we have. We have strontium fluoride is going to split into strontium ions and 2 fluoride ions. Okay, 2-to-1 ratio. This time, the solubility is going to be the concentration of strontium times the concentration of fluorine squared, because it's coefficient 2, so it becomes the exponent. It tells us that this number is 2.5 times 10 to the negative 9. Okay, I'm just going to write this again. So if I made like an ice box, strontium fluoride turns into strontium plus fluorine. Initially, there would be 0. All right, so initially 0. The change, this is going to gain some. It's going to dissolve and some strontium will form. so plus x. This is going to gain twice as much because it's a 2-to-1 ratio. So the gain here is going to be 2x. So when I solve for my equilibrium, this is x and this is 2x. So when I plug them in over here, strontium is x and fluorine is 2x. But look, it's also squared. So we're doubling it and squaring it. So what's going to end up happening is we're going to get 2.5 times 10 to the negative 9 equals x times 4x squared. So you square both parts. So this ends up being 4x cubed. All right. So when it's not a 1-to-1 ratio, it gets a little bit more complicated. So now as you solve for x, we have to divide by 4 and then take the cubed root, not the square root. So I'm going to do 2.5 times 10 to the negative 9. I'm going to divide by 4. Then I'm going to take the cubed root of that answer because I'm undoing a cube. So cubed root, last answer, comes down to 8.55 times 10 to the negative 4. Okay, so if I plug that in, X is the concentration of strontium. So strontium is going to have that answer, 8.55 times 10 to the negative 4. Fluorine is going to be a 2x. So it's twice that answer. So I have to multiply that by 2, and I get 0.0017. All right, so you can either write it as 0.0017, or if you like scientific notation, it'd be 1.7 times 10 to the negative 3. Okay, it also asks for strontium fluoride. Well, strontium fluoride is just X because coefficient 1, coefficient 1, coefficient 2. So these two are going to have the same answer. So the concentration of strontium fluoride will be the same as the concentration of strontium because it's a 1-to-1 ratio. So this will also be 8.55 times 10 negative 4 molar. So these are the answers that are asked for in number 6. Okay, let's stop there and see if you guys can solve, if it starts to make sense now. Let me know if that doesn't help or you need more clarification. Adios, amigos.